Hello, good day everyone. We are electronics engineering students from the Polytechnic University of the Philippines. Today we will be learning all about solar energy applications. This discussion will start with an introduction and will contain topics about flat plate solar collector, concentrating solar collector, solar power tower plant, solar pond, photovoltaic cell, and lastly passive solar application.
A pleasant day to all the viewers of this presentation. At this point, we are now going to discuss about solar energy applications. Now, we shall begin the discussion by talking about solar energy. So over the years, we've seen a continuing interest in solar energy, as attested by the numerous literature and studies that were published about it. But this does not come as a surprise because 1. Solar energy is free. One can readily derive it from the sun, an energy source that is not monopolized, at least as of this date. In addition, solar energy is also non-polluting, meaning utilization of solar power does not emit greenhouse gases or harmful wastes. Such attractive attributes of solar energy, however, does not necessarily make it free from disadvantages. First of all, solar energy requires a lot of space. Solar collectors, which are devices used in solar energy systems to collect and concentrate solar radiation, come in huge sizes. Another disadvantage is that solar systems are costly. Since components of solar systems take up space, it only makes sense that installation of these systems would demand a lot of money. In addition, some solar energy applications, such as cooling systems and storage systems for nighttime use, would require integration of additional devices, which entails added cost. Limited availability is also a disadvantage. While an argument that no one monopolizes the sun was made earlier, solar energy is only available in reasonable quantities in certain location and time. Now, the presence of these disadvantages only means that as further solar energy-related developments are made, the need to utilize existing technologies such as artificial intelligence, blockchain, Internet of Things, and automation, among others, also grows. Doing so allows one to make the best out of these solar systems. Now, when one harvests solar energy, they usually intend to use it for a certain application, which would require converting it to a certain usable form. When solar radiation is converted to fossil fuel or biomass, which is essentially photosynthesis, the conversion process is heliochemical. When solar radiation is converted to a usable form of heat, the process is heliothermal. Heliothermal process is the process to go for in applications that involve space heating and cooling, and also for the production of hot water. Finally, when solar radiation is converted directly to electricity, the process is called helioelectrical. Photovoltaic or solar cells carry out helioelectrical process. When talking about solar engineering process, it is important to note that it is usually categorized into two, active and passive. What sets these two categories apart is simple, the use of mechanical or electrical operation and devices. For active process, mechanical or electrical operation and devices is present. On the other hand, passive process does not require such operation and devices. So as we dive deeper into the discussion, it is important to note that when we're talking about solar energy applications, we're usually talking about the special devices that are used to capture solar energy to produce useful energy.
Now we are going to explore flat plate solar collector, which I believe most of us are already familiar with. As the name implies, it is used to produce useful heat from solar energy. For example, they are utilized to produce hot water, which are commonly used in cleaning and taking a bath. Space heating is also one of its uses. It's just that most solar heat is available during summer when space heating is not needed. Solar collectors are also very common in Southern Europe and Asia because of the abundant availability of solar energy which is present for more than 200 days a year. To understand flat plate solar collector better, we can see here a thermosiphon solar water heater system which operates on a natural circulation. Here, water flows through the system when warm water rises into the tank as cooler water sinks. On the other hand, an active closed-loop solar water heater, which we can see here, uses a pump for the circulation of water containing antifreeze fluid. This antifreeze fluid is what ensures that there is no freezing in sub-freezing temperatures. So how does it work? The water with antifreeze fluid is heated in the collector. It gives up its heat to water in a heat exchanger. Then, the resulting hot water is used in the residence. When solar energy is not available, this system still works through the use of electric resistance heater. Now, some may be wondering how does this flat plate solar collector really works. We can see here the cutaway view of a flat plate solar collector. It consists of a glazing, an absorber plate, flow tubes, insulation, glazing frame, and a box enclosure. The absorber plate absorbs solar energy transmitted through the glazing, which is a type of glass. Flow tubes are attached to the absorber plate and water is heated as it flows in the tube by absorbing heat from the absorber plate. The sides and back are insulated to minimize heat losses. Now, let's proceed with the important formulas or equations that we will encounter when reading about solar collectors. The first one is the formula for the rate of solar heat absorbed by the absorber plate, which is equal to tau alpha Ag, where tau is the transmissivity of the glazing, alpha is the absorptivity of the absorber plate, A is the area of the collector surface, and G pertains to the solar insolation or irradiation, or the solar radiation incident per unit surface area. If there is solar heat absorbed by the absorber plate, there is also heat loss from the collector by convection to the surrounding air and by radiation to the surrounding surfaces and sky. The rate of heat loss can be expressed as UA times the difference of T sub C and T sub A, as we can see here. U pertains to the overall heat transfer coefficient, A pertains to the area of the collector surface, while T sub C is the average collector temperature and T sub A is the ambient air temperature. Next, to find the useful heat transfer to the water, we can use two formulas. The first one is by subtracting the rate of heat loss from the rate of solar heat absorbed. Substituting the two formulas we have discussed earlier, we will arrive with this equation 1. From this, we can see that the useful heat is maximized when the difference between the collector temperature and the air temperature is minimized. But this also means that hot water is produced at a low temperature due to lower temperature of the absorber plate. We can also use the second formula if the mass flow rate of water flowing through the collector M is known. This should be multiplied to the specific heat of water and to the difference of the outlet and inlet temperature of water, as seen in equation 2 here. Moreover, the efficiency of a solar collector may be defined as the ratio of the useful heat delivered to the water to the radiation incident on the collector, as seen in this formula. The radiation incident is equal to Ag. Substituting the formula for useful heat delivered to the water and for the radiation incident, we will arrive at this equation. We can see here that the collector efficient is maximized for maximum values of transmissivity of the glazing and the absorptivity of the absorber plate. Also, the smaller the difference between the collector and air temperatures, the greater the collector efficiency. We also have another way to solve for the efficiency, which is known as Hotel-Villiers-Bliss equation, which is the equation number 2 here. It can be used when the average temperature of the collector is not available. In this equation, collector efficiency is defined as a function of water inlet temperature where F sub R is the collector heat removal factor. Obviously, the maximum efficiency is obtained when the subtrahend is 0. Another formula that can be used to find the efficiency of a solar collector is this one. The solar collector is normally fixed in position. As the angle of solar incident radiation changes throughout the day, the product of the transmissivity of glazing and the absorptivity of the observer plate also changes. This change can be accounted for by including an incident angle modifier in the Hotel-Willier-Bliss equation. Doing so, we will arrive at our third formula. Now, going back to our first equation for the efficiency of a solar collector, if it is plotted against the term T sub C minus T sub A all over G, we obtain a straight line as shown in this figure. The slope of this line is equal to negative U. The second equation is also in a linear function format if the collector efficiency is plotted against the term T sub C minus T sub A all over G. But the slope of the resulting straight line will be negative F sub R U. Moving forward, these are the typical values of transmissivity absorptivity product or the tau alpha and the overall heat transfer coefficient or U. As we can see here, an unglazed collector allows more solar radiation input to the collector due to higher tau alpha values, but also involves higher heat transfer coefficients. However, even though the tau alpha values go down slightly from no glazing to single and double glazing, the U value decreases significantly. Therefore, we can see that a single glazing collector is more efficient than an unglazed collector or the no glazing. This is why most flat plate solar collectors have single glazing. Now let's proceed with our sample problems. We have here a problem about the efficiency of a flat plate solar collector. As we can read here, the specifications of two flat plate collectors are given as follows. For the single glazing, the transmissivity is 0.96, the absorptivity is 0.96 as well, and the U is 9. For double glazing, transmissivity and absorptivity is equals to 0.93, U is equals to 6.5. The heat removal factor for both collectors is 0.95. The solar insolation is 550 watts per square meter and the ambient temperature is 23 degrees Celsius. For each collector, we need to determine first the collector efficiency when the water enters the collector at 45 degrees Celsius. Letter B, the temperature of water at which the collector efficiency is 0. Letter C, the maximum collector efficiency. We need to take the incident angle modifier to be 1. And lastly, we need to plot the collector efficiency as a function of T sub C minus T sub A all over G for each collector. Now, solving the problem, let's start with determining the collector efficiency when the water enters the collector at 45 degrees Celsius. We have two solutions here. One is for the single glazing and the other one is for the double glazing. We have already tackled the formula needed to solve this problem. Now, all we have to do is to substitute the values given in the problem. Note that the incident angle modifier is usually equal to 1. You can try to solve this using your calculators. For single glazing, the answer will be 0.534. For double glazing, the collector efficiency is 0.575. Next, to determine the temperature of water at which the collector efficiency is 0, we will still use the same formula we used in letter A, except that this time, we will set the efficiency to 0. We can transpose the second term of the formula and compute for the water temperature. The same thing can be done for both the single glazing and the double glazing. Solving this, we will get 79.3 degrees Celsius for single glazing and 96.2 degrees Celsius for double glazing. Next, to determine the maximum collector efficiency, as I have mentioned earlier, the subtrahend should be 0. Therefore, we are left with the equation maximum collector efficiency is equal to F sub R times incident angle modifier times transmissivity and absorptivity. Through direct substitution, we will have 0.876 for collector A and 0.822 for collector B. Lastly, this is the plot of the collector efficiency as a function of T sub C minus T sub A all over G. Based on the calculations earlier, the color green is for the single glazing and the color blue represents double glazing. For our next sample problem, we have here about energy and cost savings due to solar collector. As we can read here, a solar collector provides the hot water needs of a family for a period of 7 months, except for 5 months of winter season. The collector supplies hot water at an average temperature of 55 degrees Celsius, and the average temperature of cold water is 18 degrees Celsius. An examination of water bills indicates that the family uses an average of 15 tons of hot water from the solar collector per month. An electrical resistance heater supplies hot water in winter months. The cost of electricity is $0.13 per kilowatt hour, and the efficiency of the electric heater can be taken to be 93% considering heat losses from the system. Now, we need to determine first the annual electricity savings to this family due to solar collector, and second, the annual cost savings. So, to determine the electricity savings, the formula to be used will be the amount of solar water heating divided by the efficiency of the heater. To be able to solve this, we first need to find the amount of the solar water heating during a month period. The formula for this is M times C sub P, or the specific heat of water at room temperature, which is equal to 4.18, times the difference of T sub 1 and T sub 2, as we can see here. Solving this, we will arrive at 2.320 times 10 raised to 6 kilojoules per month. We need to multiply it to 7 since what we are computing is for a 7-month period. Then, we can already do direct substitution and compute for the electricity savings. To have the answer in kilowatt hour, we can use the conversion factor 1 kilowatt hour is equal to 3,600 kilojoules. Moreover, to determine the annual cost savings to this family due to solar collector, we only have to multiply the computed electricity savings to the unit cost of electricity, which is already given in the problem. You can try this on your calculator and the answer should be $631. And that's all for flat plate solar collector.
Now, what you see here on your screen is a concentrating solar collector, specifically a parabolic trough collector. Again, solar collectors are used to capture solar radiation and convert them into usable heat or to produce hot water. It is said, however, that the concentration of solar radiation is inherently low, which indicates that capturing solar radiation as is would yield a fluid whose temperature is not hot enough for major applications. As seen in flat plate collectors discussion, the typical fluid temperature generated is only around 80 degrees Celsius. In concentrating solar collectors, what happens is that solar radiation bounces off the collector surface, the one you see in color blue, and is redirected to the smaller receiver, the one you see in color red. It is worth noting that this receiver is generally made of stainless steel, which has a spectrally selective surface coating, which allows for the maximization of solar irradiation absorption. Again, just to reiterate, solar radiation bounces off the collector surface and is redirected to the receiver when it comes to concentrating solar collectors. Also, hot fluid can be produced from concentrating solar collectors. Hot fluids produced from concentrating solar collectors typically hit 400 degrees Celsius. In concentrating solar collectors, there's what's called a concentration factor, which is mathematically expressed as seen on the screen. The concentration factor is always greater than 1. This also tells us that the greater the concentration factor, the hotter the fluid generated. Now, this is the formula for the net rate of solar radiation in concentrating solar collectors. The optical efficiency variable in the equation describes the effectivity of the aperture to receiver process, which is related to the reflective and absorptive properties of the collector and receiver, respectively. Now, this is the formula for useful heat transferred in fluid, which is basically the difference between the net rate of solar radiation and the net rate of heat loss. This is the formula for the efficiency of a concentrating solar collector, which is the ratio of useful rate of heat transferred to the fluid and the incident heat. As you can see, the incident heat is equal to the product of the collector area and the solar irradiation. Now, what you are seeing in the screen is a linear concentrating solar power collector. A linear concentrating solar power collector is basically a large number of parallel rows of parallel trough concentrators that are used to direct or to collect solar heat. Mathematically, the efficiency of linear concentrating solar power collector is expressed as seen on the screen. Now let's try to solve this problem. Two concentrating collectors, collector A and collector B, have the same concentration factor of 9 and the optical efficiency of 0.85. The collector temperature for both collectors is 350 degrees Fahrenheit and the ambient air temperature is 85 degrees Fahrenheit. The heat loss coefficient for collector A is 0.45 BTU per R times feet squared times degree Fahrenheit, and that for collector B is 0.63 BTU per R times feet squared times degree Fahrenheit. The solar irradiation on collector A is 180 BTU per R times feet squared. Determine the solar irradiation rate of collector B so that both collectors have the same efficiency. Now, we can solve that problem by first determining the collector efficiency of collector A. So if you're familiar earlier, this is the equation for the efficiency for collector A. And by substituting the values, we will get a efficiency for collector A, which is 0.7764. And now using the same formula, but at this point for collector B, and using the same collector efficiency, we can obtain the necessary solar irradiation rate. Remember that what we only have to do is to substitute the values properly, and we will arrive with a solar irradiation rate of 252 BTU per R times feet squared for collector B. So that's how you solve that question.
On our next topic, we're going to talk about solar power tower plants. Electricity can be produced from solar energy by solar cells by direct conversion of solar radiation into electricity or by using parabolic through collectors. A solar power tower plant uses a large array of mirrors called heliostats that track the sun and reflects solar radiation into a receiver mounted on top of a tower. Water is heated, boiled, and superheated by absorbing heat from the receiver system. The resulted steam is directed to a turbine to produce power. A generator is combined and connected to turbine to convert turbine shaft power into electricity. The first large-scale solar power tower plant is Solar One located at Barstow, California. It has a capacity of 10 megawatts. The tower is 91 meter high, and the receiver located at the top of the tower is water-cooled. There is an oil sand storage unit that can help supply electricity for 3 to 4 hours after sunset. The total cost of Solar One plant was $14,000 per kilowatt, which is 5 to 10 times greater than the cost of electric power stations that run on fossil fuels and other renewables. The Solar 2 plant is a sister station of Solar 1, which went into operation in 1988 and uses a molten nitrate salt thermal energy storage system. The Gemma Solar Power Plant, located in Seville, Spain, consists of 2,650 heliostats that focus 95% of solar radiation onto a giant receiver. The plant started commercial operation in 2011, occupying a field of 185 hectares. The temperature as high as 90 degrees Celsius are obtained at the receiver. Molten salt tanks are heated by concentrated solar heat, reaching a temperature above 500 degrees Celsius. Water runs through the molten salt tanks, in which it is boiled and superheated. The resulting steam is directed to turbines to produce power. Steam leaving the turbine is condensed and pumped back to the molten salt tanks to repeat the heat engine cycle. The plant can store solar heat and use it for a period of 15 hours in the absence of daylight. The plant has an installed capacity of 19.9 megawatts and can produce 110 gigawatts-hour of electricity per year. This is enough electricity for 25,000 homes. Electricity is produced for 270 days a year. The cost of Gemma Solar Plant is $33,000 per kilowatt, which is even higher than that of Solar One. Ivanpah Solar Power Plant started commercial operation in 2013 after a 3-year construction period and consists of 3 separate units. The electricity generated can serve 140,000 homes during the peak hours of the day. The plant is located in Mojave Desert in California and is the largest solar thermal power plant in the world with a capacity of 377 megawatts. It is located at an area of 3,500 acres with 300,000 concentrated mirrors reflecting solar energy to receivers at the top of the tower in 3 plants. The towers are 140 meter high. The solar energy is absorbed by water flowing in the pipes of the boiler. The water turns into superheated vapor, which is directed into a steam turbine located at the bottom of the tower. Electrical output from the turbine is sent to transmission lines. This plant uses air-cooled condenser, which uses 95% less water than wet-cooled solar thermal plant. Now for the problem solving, let us take a look at this problem. A solar power tower plant is considered for Tucson, Arizona. Heliostats with a total area of 80,000 meters squared are to be used to reflect solar radiation into a receiver. When the solar irradiation is 950 watts per meter squared, steam is produced at 2 megapascals and 400 degrees Celsius at the rate of 20 kilograms per second. This steam is expanded in a turbine to 20 kilopascal pressure. The isentropic efficiency of the turbine is 85%. A. Determine the power output and the thermal efficiency of the plant when the solar radiation is 950 watts per meter squared. B. How much electricity can be produced per year if the average thermal efficiency is 15% and the generator efficiency is 96%? We have to remember that the performance of an actual turbine or pump is usually expressed in terms of isentropic efficiency. Isentropic efficiency of turbine is defined as the ratio of work delivered by actual turbine to work delivered by an isentropic turbine. Since the isentropic efficiency is given as well as the work delivered by the actual turbine, we will be solving for the energy from the work delivered by an isentropic turbine, which yields 2,484.5 kilojoule per kilogram, which will then be utilized to solve for the output power, which is the power of mass and the work delivered by the actual turbine, which yields 15,280 kilowatts. And the thermal efficiency of the power plant is equal to the power output divided by the total solar incident on the heliostats, which yields 20.1%. In this scenario, we will be solving for the power output, which is the product of the given thermal efficiency and the total solar incident on the heliostats. The daily average solar irradiation for an entire year on a horizontal surface is given to be 20.44 megajoule per meter squared. Multiplying this value with 365 days of the year gives an estimate of solar irradiation on the heliostat surfaces. This yields a power output of 2.487 times 10 raised to 7 kilowatt-hour. The total work output from the turbine multiplied to the generator efficiency will yield the electrical energy output from the generator, which will be 2.387 times 10 raised to 7 kilowatt-hour as solved. Now we are going to tackle about the solar pond. A promising method of power generation involves collecting and storing energy in large artificial lakes a few meters deep, called solar ponds. Solar energy is absorbed by all parts of the pond, and the water temperature rises everywhere. The top part of the pond, however, loses to the atmosphere much of the heat it absorbs, and as a result, its temperature drops. This cool water serves as an insulation for the bottom part of the pond and helps trap the energy there. Usually, salt is planted at the bottom of the pond to prevent the rise of this hot water at the top. A power plant that uses an organic fluid such as alcohol as the working fluid can be operated between the top and the bottom portions of the pond, as shown here. However, the main disadvantage of a solar pond power plant is the low thermal efficiency. For example, if the water temperature is 35 degrees Celsius near the surface and 75 degrees Celsius near the bottom of the pond, the maximum thermal efficiency can be determined to be 11.5%. Actual thermal efficiency will be less than this value. Small experimental solar pond power plants have been installed. Several practical problems such as mixing of pond water and the wind and falling of heat exchanger surfaces exist in addition to low thermal efficiency. An ocean thermal energy converter or OTEC system uses the same principle, but the water at the sea or ocean surface is warmer as a result of solar energy absorption, and the water at a deeper location is cooler.
Now, we talk about photovoltaic or solar cells. As mentioned earlier, photovoltaic cells implement a helioelectrical process, which means that solar radiation is directly converted to electricity through the use of these cells. As indicated, an array of solar cells is sufficient enough to compose a photovoltaic system. It is also worth noting that silicon is commonly used as the main material in solar cells, although its efficiency is only at about 15 to 20%. Also take note that a single solar cell only produces around 1 to 2 watts of power. Since a singular solar cell can only provide a relatively low power, there is a need to combine them together to make them applicable for higher power applications. So when we have this, which is once again a photovoltaic cell, then when we configure them in a serial fashion, we will get a module. When modules are configured to be in series with each other, what we get is a string. And when we have modules in a parallel fashion, we form an array. Now, gaining a basic understanding of solar cells requires one to have a good grasp on the concepts of semiconductor and atomic theories. Mathematically speaking, the principle of solar cells is founded on this equation, which tells us that the light-induced recombination current, J sub R, is equal to reverse saturation current, J sub O, multiplied to E, raised to the ratio of the charge of an electron multiplied to voltage V, to the Boltzmann constant K, multiplied to cell temperature. To further elaborate, we now see a simplified model of a solar cell which involves p-type semiconductor and an n-type semiconductor. It is depicted here that there is a current density flow at the p-n junction of a solar cell. If the model is converted into a circuit diagram representation, this is what we will get. We can see here the presence of current output density J sub S, load current density J sub L, and junction current density J sub J. It is worth noting that the junction current density is equal to the algebraic sum of light-induced recombination current J sub R and reverse saturation current J sub O. Now, by employing proper circuit analysis methods, we can derive the pertinent equations for solar cell-related calculations. So first, here's the equation for open circuit voltage. Then we have the equation for the ratio of load current density and short current density ratio. We also have the equation for power output delivered to the load. And finally, we have the equation for the conversion efficiency of a solar cell. By properly establishing a relationship among the previous equations, we can derive this graph. Basically, this graph tells us that the power output from a photovoltaic cell is proportional to solar radiation absorbed by the cell. We can also see that as it turns out, as the solar irradiation increases, the load current also increases, but the increase in open circuit voltage is small.
Now we are done with our last topic under solar energy applications, which is the passive solar applications. This one is different from what have been discussed earlier, like the solar collectors and photovoltaic cells that represent active solar applications. When we say passive solar applications, we are dealing here with the use of solar energy by means of engineering design without the involvement of mechanical equipment. Examples are solar heating of swimming pools, food drying, and solar cookers. Other common examples are drum walls and solar heat gain through windows, which we will tackle. The dark painted thick masonry walls you can see here in this picture is what we call the Trump wall. It is proposed by E.L. Morse and named after Professor Felix Trump of France, who used it extensively in his designs in the 1970s. It is commonly used in south side of passive solar homes. So what we need to understand here is that this Trump wall absorbs solar energy, store it during the day, and release it to the house during the night. That's why it is particularly effective in reducing heating energy consumption for mild winter climates. So to better understand how this works, this picture here is a good reference. Next, what we have here is the solar heat gain through windows. We can see in this picture the direct radiation, diffuse radiation, and radiation reflected onto the surface from surrounding surfaces. The direct radiation pertains to the part of solar radiation that reaches the Earth's surface without being scattered or absorbed, as we can see in this figure. On the other hand, diffuse radiation is the solar radiation that is scattered or emitted by the constituents of the atmosphere. Moreover, if we want maximum daylight and minimum solar heat gain, we need a glazing material that transmits the visible part of the spectrum while absorbing the infrared portion. Ordinary window glass like what we have in this slide is perfect. As we can see here, when solar radiation strikes a glass surface, part of it is reflected back to outdoors. Other part is absorbed within the glass and the remainder is transmitted indoors. Here, the reflected part is 8%, transmitted part is 80%, and the absorbed part is 12%. Moving forward, let's have the solar heat gain coefficient or SHGC. The sum of the transmitted solar radiation and the portion of the absorbed radiation that flows indoors is what constitutes the solar heat gain of the building. The fraction of incident solar radiation that enters through the glazing is called the solar heat gain coefficient or the SHGC and is expressed as shown here. It is equal to tau sub S plus F sub I times alpha sub S, where tau sub S is the directly transmitted portion of solar radiation incident. Alpha sub S is the solar absorptivity of the glass, and F sub I is the inward flowing fraction of the solar radiation absorbed by the glass. The value of SHGC ranges from 0 to 1, with 1 corresponding to an opening in the wall or the ceiling with no glazing. Moreover, if the SHGC of a window is already known, the total solar heat gain through that window can be determined by SHGC times A sub glazing times G, wherein A sub glazing is the glazing area of the window and G is the solar heat flux incident on the outer surface of the window. Next, we have another way of characterizing the solar transmission characteristics of different kinds of glazing and shading devices. It is to compare them to a well-known glazing material that can serve as a base case. Therefore, shading coefficient is equal to SHGC over SHGC reference, the standard 3 mm thick double-strength clear window glass sheet whose SHGC is 0.87 will serve as our reference glazing. Next, we have here the shading coefficient and solar transmissivity of common glass types for summer design conditions. One thing to remember is that the larger the shading coefficient, the smaller the shading effect, and thus, the larger the amount of solar heat gain. Moreover, the values for winter design conditions may be slightly lower because of the higher heat transfer coefficients on the outer surface. Now, what are shading devices? These are used to control solar heat gain through windows. We have two types, the internal shading and the external shading. External shading devices are more effective in reducing the solar heat gain since they intercept the sun rays before they reach the glazing as seen in our example. It is a properly sized overhang which blocks off the sun rays completely in summer while letting them through in winter. On the other hand, internal shading devices reduce solar heat gain by reflecting the transmitted solar radiation back through the glazing before it can be absorbed and converted into heat in the building. Common example is a drape as shown in this figure, which we are all familiar with. Moving forward, the type of climate in an area is what commonly dictates the type of windows to be used in buildings. In cold climates where the heating load is much larger than the cooling load, low-E windows are well suited for heating-dominated buildings. In warm climates where the cooling load is much larger than the heating load, the windows should allow the visible solar radiation in but should block off the infrared solar radiation. Window glazings that are coated with a heat-absorbing film outside and a low-E film inside like what is seen here is good to use. Now we have here our last sample problem, which is about cooling energy consumption of a house for two windows options. Two window options are considered for a new house with a floor area of 250 square meters. Windows occupy 16% of floor area and equally distributed in all four sides. Windows options are, first, double glazed window, clear glass, airfill, U factor is equals to 4.18 and SHGC is equals to 0.77. Option number 2, we have double glazed window, low E glass, argon gas fill, U factor is equals to 1.42 and our SHGC is 0.39. The average daily solar heat fluxes incident on all four sides is given in kilowatt-hour per square meters times day during summer cooling months as follows. For June, we have 4.95, for July, we have 4.80, for August, we have 4.55, and for September, we have 3.95. Now, we need to first determine the total amount of heat gain through the windows in summer. Take the average outside and indoor temperatures in summer to be 35 and 23 degrees respectively. Second, if the coefficient of performance or COP of the cooling system is 2.3, determine the net cooling cost savings in summer due to using window option 2. Take the unit cost of electricity to be $0.11 per kilowatt-hour. So first, to determine the total amount of heat gain through the windows in summer, we first need to find the total window area, number of hours in summer months, and total solar heat flux incident on the glazing during summer months. The steps here are pretty simple and are already shown. You can try it and see if you will get the same answers. Now, to calculate for window option 1, we only need to add the amount of heat transfer through the window and the solar heat input. Formulas are already provided on how to solve for these two. You just have to do direct substitution. Feel free to solve it using our calculator. The answer should be 23,028 kilowatt-hour. For window option 2, the steps and formulas are still the same, but take note that the given U factor and SHGC are different from window option 1. Solving this, we will arrive at 10,684 kilowatt-hour. Lastly, we need to determine the net cooling cost savings in summer due to using window option 2. To solve this, our formula is cooling load decrease times unit cost of electricity all over the coefficient of performance. These are all given except for the cooling load decrease. To get that, we just have to subtract our answers earlier. Total amount of heat gain of window option 1 minus total amount of heat gain of window option 2. Then, substituting all the given and computed values, we will arrive at $590 cooling cost savings as we can see here.
And that is all for our report about solar energy applications. Once again, we are electronics engineering students from the Polytechnic University of the Philippines. These are my co-reporters, Raniel, Brando, Guia, Kristine Marie Manansala, and yours truly, Charisse, Jenn, Hobrero. We hope you've learned a lot from this video and thank you so much for staying with us. Bye!